All right, so we want to interpolate predictions using the expression y equals mx plus b. So extrapolation and interpolation are two categories of predictions. They're mathematical predictions, to be exact, or data predictions. And let's examine these concepts using this candle experiment. So we have a ruler, a candle, and a stopwatch. We're going to start the stopwatch, and we're going to measure how high the candle is as it's burning. So this is going to be our dependent variable. This is what we're measuring, and it's dependent on how much time is passing and how much it's being burned. So here's our graph on the right. Interpolation is a prediction within given data points on a scatter plot. So within. So let's look here. So here's our data. We have a data point here at 0, 17, and we have a data point at 150, about 9.5. So anytime you make a prediction that's in this range of data, that is interpolation. I should keep these consistent. I'm going to make this in red. Interpolation in red, extrapolation in green. Okay, so extrapolation. Extrapolation is a prediction outside given data points on a scatter plot. Outside. So if you're ever making a prediction about this data and you're falling into this range down here, you can still use your trend line to make predictions. However, this would be considered extrapolation if you are in this range of data prediction. So it is thought to be a little bit less reliable, maybe a little bit less accurate if you are making predictions for outside of the data that you actually tested. So usually extrapolation is less reliable than interpolation. So let's actually do it. So let's interpolate, let's predict the height of the candle after 120 minutes of burning. So let's look here. After 120 minutes of burning, I'm interpolating, I'm going to be in red here. Here's 120 down here. 120 minutes of burning. I move up to the trend line and over, and I see that I am at a height of 11 centimeters of height. So after 120 minutes of burning, the candle will be 11 centimeters in height. So remember to always, when you're in, to always use the trend line. Don't use your data points, but use the trend line itself. So up to the trend line and over. Predict the height of the candle after 260. I think this was a typo. Cross this out and write 270, right? 270 minutes of burning. So after 270 minutes of burning, the candle will be, how high will this candle be? So let's go to 270, 50, 70, bing, and over, bing. Our height is 3 centimeters. So this height has gone down quite a bit. 3 centimeters, or so we would predict, because we are in the less reliable range. We are extrapolating data. We are not interpolating data because it's outside the range of tested data. Cool. So that's the concept of interpolation and extrapolation. Now the next thing is we're going to use the equation y equals mx plus b. Y equals mx plus b. And remember that m is the slope and b is the y-intercept. So let's look at what b is in this graph really quick. So I'm going to do this in orange. So b equals 17. Y, here's my y-intercept. And here's my line. The line intercepts at 17 centimeters. The line intercepts at 17 centimeters. So that's what I'm talking about when I'm using this symbol. B stands for the y-intercept. Now m is slope, and so what's the slope of this line? Let's use these little lattice points that we sort of already looked at here. So if we draw a triangle to do the rise over the run, the rise is 1, 2, 3, 4, 5, 6, 7, 8, so 8, and then counting by 20s, 20, 40, 60, 80, 100, 120, 140, 160, 180, 180. That means that the slope, the rise over run, so slope, is the same as m, which is going to equal the rise over the run, 8 over 180. So we have the value for m, and we have the value for b, and so we can rewrite our linear expression. I'm going to rewrite it right below. Y equals 8 over 180x plus 17. So that is a nice little linear equation. You could reduce that slope value, that m value, if you want to be extra cool. So let's utilize the expression y equals mx plus b. M stands for slope. B stands for y-intercept. I've seen it before as growth and starting point. That's fine too, as long as we're all talking about the same thing. So it says the equation for the trend line on the right is y equals 2.5x plus 2. So we got this experiment here. Number of tomatoes per plant and the hours of exposure to sunlight. So as the plants get exposed to more sunlight, these plants are going to have more tomatoes growing on them. That makes sense, right? Plants need sunlight to grow and to make stuff like tomatoes on them if they're a tomato plant. So it's saying that this is the equation. So if this is the expression here. So if that's the case, then this is our y-intercept. This is our y-intercept. And our slope here, that's 2.5. So it's saying that if we're going to continue this line, it's going to hit at around 2. Cool. And it also is telling us that the rise over run, rise divided by the run, that's going to equal 2.5. Okay, let's do 3 just quick math problems. Making a prediction using the equation. How many tomatoes per plant will be found when exposed to 3.5 hours of sunlight? So we want to substitute the value of the independent variable for x, and we want to solve for y. So here's our graph here, and it's saying what will happen, how many tomatoes per plant do you get when you are exposed to 3.5 hours of sunlight. So this is our value, or number, of the independent variable, hours of exposure to sunlight. So we're going to substitute that in for x, and then solve for y. Y equals 2.5, and instead of writing x, I'm going to substitute in 3.5. And then I got to keep that plus 2 because that's my other part of the expression or linear equation. And then I just solve. Y equals 8.75. That's 2.5 times 3.5 plus 2. Y equals 10. But in physics, you never forget your units. And 10 tomatoes per plant. So does that make sense? Or 10.75. So if we're at like 3.5 and we're going over, yeah, it's about 10.75. Cool. So, oops, 10.75 tomatoes per plant. Tomatoes, however you'd like to say it. It also works backwards. So say you find a plant with 15 tomatoes on it, or you find plants with 15 tomatoes per plant. How much sun have these plants been getting? Okay, so we're going to substitute for this one. It's giving us the dependent variable. So we're going to substitute the value of the dependent variable for y. So it didn't give us the independent variable, and it didn't tell us how much sun there is. It told us how many tomatoes per plant there is, so we're just going to work it backwards. So if we have 15 tomatoes, that's instead of writing y, I'm going to write 15 equals mx plus b, 2.5x plus 2. We have a little math problem here, so I'm going to subtract 2 on both sides. I get 13 equals 2.5x. Going to divide by 2.5 to cancel these out. Whatever I do to one side, I do to the other. You know your homie algebroni. And then 13.5 divided by, or 13 divided by 2.5. I wish I could do that in my head. I just can't. 13 divided by 2.5. 13 divided by 2.5 equals 5.2 equals x. So what are our units here? Well, our x value, or our independent variable, is hours of sunlight. Hours of sunlight. So there you have it. It works backwards too. So you can make these predictions using y equals mx+b forwards and backwards. So if we are in 5.2 hours of sunlight, 5.2, it should get to 15. Cool. You know, and this is all considered interpolation. What color did I use for interpolation? Red. These two things would be interpolation, because there's my lowest value, there's my highest value. Because I'm in this range here, we hit this 3.5 hours of sunlight, and we hit these 15 tomato plants. So that's interpolation. We're within the data range. It's an example of interpolation. Okay, let's just do one example of extrapolation and be done with it. One more. How many tomatoes per plant will be found when exposed to 15 hours of sunlight? So now our graph doesn't even go up to 15, it goes up to 7, but we want to substitute 15 hours of sunlight, the value of the independent variable, for x in our equation. So solve for the dependent variable, or y. Okay, so easy peasy lemon squeezy. Let me just write it here. Y equals mx plus b. That's the basic linear expression, but we have y equals 2.5x plus 2. That's the equation for this specific graph. And we are now going to input 15 hours in, and hours of time or sunlight exposure. That's our independent variable, so we're going to plug that in for x. Y equals 2.5 times 15 plus 2, and then we just solve. 2.5 times 15 plus 2 is 39.5. 39.5 tomatoes. Oh, these are such healthy tomato plants. Tomatoes per plant. Think of how delicious this would be after you just get to do these math problems and then enjoy, I don't know, some pasta with tomatoes on it. Oh my gosh. And this is an example of extrapolation. Why is it extrapolation? We're outside the given data point. We did not measure any 15-hour tomato plants. We just used the math and we made a prediction. So hopefully if you wait long enough, wait some 15 hours, you'll have around 39.5 tomatoes per plant. That's how you do it.